These are the Lesson 9.1 notes, direct and inverse variation. Today what we're going to do is we're going to write direct and inverse variation functions that pass through a point. We're also going to solve multiple variation problems. So what is this thing called variation? The idea of direct variation is the idea that as x increases, y increases. An example might be the more water we put in a water balloon, the more it weighs. And consequently, the less water we put in a water balloon, the less it weighs. Inverse variation means that as x increases, y decreases. The more speed I travel at, the less time it takes to get home. The faster I go, the less time it takes. Vice versa as well. The slower I go, the more time it takes for me to get home. So we're going to look at problems that have both direct and inverse variation. Let's take a look at this first problem. It says find a direct variation function that passes through the point 2, 0 or 2, 6. When we're writing the general form of a direct variation function, what it's going to look like is this. A direct variation function is going to be in the form y equals k times x. K is a constant that is going to be replaced by a number in just a few minutes. To solve for k in this problem, what we're going to do is we're going to substitute the points 2 and 6 into our equation. So we're going to plug in 6 for y and we're going to plug in 2 for x. And then we're just going to solve this little equation for k. Pretty easy, divide both sides by 2 in this equation. You get a 3 on the left side and we get a k on the right side. So when we rewrite our equation, I'm going to replace the k with a 3. And it's going to look like y equals 3 times x. We're going to make a table of values for our direct variation function so you can see that as x gets bigger, so does y. So if we multiply each of these x values by 3, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15, 3 times 6 is 18. And you can definitely see this relationship as x gets bigger, as x increases, y increases as well. Now something else that's kind of interesting about the relationship between these values is that each of these xy pairs, if you look at 1, 3, 2, 6, 3, 9, 4, 12, 5, 15, 6, 18, each xy pair has the same, well, if you think of these as fractions, 1/3 is the same as 2/6, which would be the same as 3 over 9 or 4 over 12. Each xy pair we say has the same quotient, which means that when you divide these numbers, whether it be x divided by y or y divided by x, you would get the same thing. If you divided 3 by 1 or 6 divided by 2 or 9 divided by 3 or 12 over 4 or 15 over 5 or 18 over 6, each of these quotients would equal 3. So that's an example of a direct variation problem. We're going to take a look at an inverse variation problem as well and see how things compare. First of all, the general form of an inverse variation function will always look like y equals k divided by x. So in an inverse function, you'll see this kind of divide by problem. If it's a direct problem, it's a multiplication. So if we're working with a point 2, 6, if we plug in 6 for y, and we plug in 2 for x, we're going to solve this equation for k. This is pretty easy to get k by itself. We need to get rid of this 2. It's being divided, so to cancel out the dividing by 2, we multiply both sides by 2. We obviously cancel out on the right side of the equation. On the left side we have 12, and on the right side we have k. So to rewrite this equation, we plug in 12 for k. And we get y equals 12 over x. So this is our rewritten model. What we're going to do next is we're going to plug in each of these x values into this equation. If we do 12 divided by 1, we get 12. If we do 12 over 2, we get 6. 12 divided by 3 is 4. 12 divided by 4 is 3. 12 divided by 5, if you're not sure what that's equal to, you can leave it as a fraction. Or if you want to type it out in your calculator and get a decimal value, that's fine as well. 12 divided by 5 is equal to 2.4. And then finally, 12 divided by 6 is equal to 2. if you compare each of these values, first of all, as x gets bigger, you'll notice that the y values get smaller. So as x increases, y decreases. And each xy pair does not have the same quotient. Obviously, 3 divided by 4 is not the same as 4 divided by 3. But if you look at each pair of numbers here, 1 and 12, 2 and 6, 3 and 4, 4 and 3, I think you'll notice it was 6 and 2 as well. If you multiply x and y together, it looks like you're always getting 12. So we say that each xy pair has the same product. So for problems that you're going to look at tonight, same kind of idea. Here's a situation where it says, suppose that x and y vary inversely. If x equals 30 when y equals 4, write a function that models this inverse variation and find y when x equals 10. Sounds like a lot of things, but it's basically the same thing that we just did. If the problem says that x and y vary inversely, remember that we're always going to start off with our general form. Y equals, if it's an inverse problem, k divided by x. If it says x and y vary directly, then you would write y equals k times x. So you're always going to start with this. The next step we're going to do is we're going to take the information in the problem, if x equals 30 and y equals 4, and we're going to write a inverse variation function based on these values. So we're going to substitute 30 for x and 4 for y. Our goal is to figure out what k is and then plug k into this equation. So to get k by itself, we need to multiply both sides by 30 here to cancel out the 30 on each side. 30 times 4 is equal to 120. And that's what k is equal to. We're going to replace the k in this problem with 120. And we get y equals 120 divided by x. So this is our function that models the inverse variation. Now we need to find y when x equals 10. So here's our equation. Plug in 10 for x. Y equals 120 divided by 10. If you understand the idea that the zeros would cancel out when you're dividing by 10s, just get 12. So two things you need to make sure you include in your answer are both the function and what you get for y when x equals this particular value. Multiple variation problems. In our next problem, it says, suppose that z varies jointly with x and y. Jointly means directly with multiple variables. So if z varies jointly with x and y, it means that z varies directly with x, and it also varies directly with y. When x equals 7, y equals 2, and z equals 28. Find z when x equals 6 and y equals 24. So for all the problems we're looking at today, we're always going to start with a general form. We're going to solve for k, and we're going to substitute some values in to figure out what our missing variable is. The general form for this function, if it says z varies jointly, that means varies directly, so it's going to be a k times problem, but it's going to be k times x times y. So we're not going to do like k times x times k times y. It's just going to be this always a single k value that we're going to try to be working with. Solve for k and rewrite. So we have this series of different values that we're going to evaluate here. X equals 7, y equals 2, z equals 28, and we'll try to solve for k. Again, this really shouldn't be too bad. You can multiply 7 times 2, that's 14. And then to get k by itself, obviously we'll divide both sides of the equation by 14. 28 divided by 14, that's equal to 2, and that's what k is equal to. We're going to rewrite our function by substituting 2 in place of k. So our equation is going to be z equals k, which is 2, xy. In our bottom problem, it says find z when x equals 6 and y equals 4. So in our problem, to find z, we're just going to replace the x with a 6 and 4 for y. And when you multiply this together, 2 times 6 is 12. 12 times 4 is 48. And there's our solution. Two parts that you want to be making sure that you always include here are the rewritten formula and obviously answering the question. Here, in particular, we're just looking for what z is equal to. Finally, z varies directly as x and inversely as the cube of y. Then when x equals 8, when y equals 2, z equals 3. Find z when x equals 6 and y equals 4. What does the general form look like here? We're going to start with z again. Varies directly. Now, if it just said z varies directly as x, you would write z equals k times x, and we'd be done. But then it says, and inversely as the cube of y. So inversely means we're going to have this division, and the cube of y means y cubed. It doesn't mean the cube root. This says the cube of y. If it said the cube root, it would write root here. The cube of y just means y cubed. So here's our general form. Now we're going to substitute our numbers in to solve for k. So we know x equals 8, y equals 2, and it's going to be cubed, and z is equal to 3. Now, I would crunch out what 2 cubed is equal to. 2 times 2 times 2, that's equal to 8. So we have 3 equals k times 8 divided by 8. Now, in this situation, the 8's would actually cancel out, and you would get k equals 3. In a lot of problems, you won't have the same numbers here and here. So if that was the case, what you could do is to cancel out this 8 in the denominator, you could multiply both sides by 8. And you would get 24 on the left side equals k times 8. And then you could divide both sides of the equation by 8. Now we already know what we're going to get here. We're going to get 3. So our equation, when we rewrite our equation here, it's going to look like z equals 3x over y cubed. Because we substituted 3 in place of k. Now what we're going to do is we're going to find z when x equals 6. So we're going to do 3 times 6 divided by 4 cubed. 3 times 6 we know that's 18. 4 times 4 is 16, times 4 is 64, so 4 cubed is 64. You can leave your answer in this form, that's okay. It is possible to reduce this fraction down to 9 over 32. If you demand a decimal value for this problem, you can just do 9 divided by 32 on your calculator, and you get 0.28125. And that gives you an idea of how to do direct and inverse variation and joint or multiple variation problems as well.